In this video, we will talk about the stability analysis of Lax-Wendroff method. For stability, we know that we have to use the Fourier analysis. And here you can see that this is the expression for Fourier analysis, only one mode of Fourier analysis. Q hat k is the amplitude of the wave and exponential is the sine and cos waves. We put this into the Lax-Wendroff method. Probably you know that the Lax-Wendroff method is un plus 1 j is equal to un j minus c by 2. C is the Courant number, and then we have un j plus 1 minus un j minus 1 plus c square by 2. C is the Courant number, and we have un j plus 1 minus 2 un j plus un j minus 1. So this is the Lax-Wendroff method. We put this Fourier mode into the equation. On the left hand side, wherever we see the n plus 1, the new time level, we put this value over here, and we also replace the amplitude with n plus 1, that is n plus 1, and we keep the exponential part same. We do not change it. And when we put this Fourier mode over here, then you need to change the xj plus 1. Since there is a j plus 1, so this j plus 1 will change, and xj plus 1 will be equal to xj plus delta x. So we put all these values over here in this Lax-Wendroff method. Since you can see that there are e raised to power iota k xj common, this is over here. When you take a common from here, this can be written as e raised to power iota k xj plus delta x. And you can see that this is the common over here, e raised to power iota k xj from here. So we can cancel out that term. Then we have, for example, probably you don't need to write the n plus 1 over here. We don't require that. K plus 1. So you can write q hat n plus 1, so on. Okay, after cancelling out the e raised to power iota k xj, we put the formula, we just simplify it, and we put the formula for e raised to power iota theta, and e raised to power iota theta is cos theta plus iota sine theta. So here we have, for example, I just cancelled out few terms over here. This will be cos k delta x plus iota sine k delta x, and then we have minus cos k delta x plus iota sine k delta x for the second term over here. These two terms will be cancelled out, and we get iota sine k delta x and iota sine k delta x, which is written over here. And we do the same for these two exponential terms. We just add these two cos and sine, so sine will be cancelled out, and we get 2 cos k delta x minus 2. After some simplification, we have, for example, We take q hat and k as a common, and we write this equation as like this. Okay, at the end, we have a amplification factor. This term is the amplification factor, and we usually call it gk delta x. Some people also write this as G, capital GK delta. It is fine until it is in an amplification factor. Since this amplification factor increases the next value, it depends on this amplification factor whether the new value will be increased or it will decrease. So this is called amplification factor. Since we don't want our solution q hat n plus 1 is equal to g of k delta x q hat n k plus 1 and n k, there is a connection between this new solution and the old solution, and this connection is through this amplification factor. And if the new value has a large value, if it is increasing, the value is increasing, then it means that this amplification factor is such that which make the solution more amplifying. So the amplification factor should be less than 1 so that the solution do not increase, or stability wave do not increase, we should say. So this is amplification factor over here. We take a mod and square so that we take a magnitude. We want to find the magnitude of that amplification factor. After some simplification, you can apply a minus b whole square, the formula for a minus b whole square. And then you can see that we also have sine k delta x. Sine k delta x can be written as 2 sine k delta x over 2 and cos k delta x over 2. And we also take a square, so it becomes 4 sine square cos square, which is written over here. So you can see that after now we have a common terms, all the terms have k delta x. Otherwise, here in the angle we have k delta x by 2, and here we have k delta x. So what I do, I just take a common 1 minus 4 c square sine square k delta x by 2, and from here, and from this term, and that term remain over here. Then we have, for example, after some simplification, this becomes, for example, sine square k delta x by 2. We take common 1 minus 4 c square sine square k delta x by 2, and we get 1 since it becomes sine 4 delta x by 2. Sine, this is 2 and this is 2, so this becomes sine 4 k delta x by 2. And then we have 1 minus c square. And c, remember that c is the courant number, which is u bar delta t by delta x. And remember that we also applying stability analysis on the advection equation, which is plus a partial u by partial x is equal to 0. If you have a over here, then we have a over here, courant number will be a delta t by delta x. For stability, this this amplification factor should be less than 1, since we have taken magnitude of that gk delta x and square. After some simplification, we multiply this with minus 1, this whole inequality with minus 1, and inequalities changes. Since this is positive, divide this 0 by 4. This will be neglected from here. Sign is always positive, so it says that uh, the this is already positive, so we have c square. We have c square 1 minus c square greater than 0. This term is positive, and if you want your answer should be 0 or positive, this should also be positive. This should also be positive. Okay. Why this can also be, there is a possibility we can have 0 or positive value if we multiply negative with the negative, but the problem is c square can never be negative, so this possibility does not exist. So the only thing we need to do is 1 minus c square should be greater than 0 so that it is positive, or 0. 0 is sometime not possible since c is a delta t by delta x. If you put this is equal to 0, then you get a delta t is equal to 0, a is equal to 0 since delta t is a number, and if a is equal to 0, it means that your advection equation is plus a partial u by partial x. This term is 0, so you get partial u by partial t is equal to 0. It means that u is, your solution is just a constant. So the magnitude of so c square should be less than 1, and c square is the current number. And when we take under root both sides, so according to this definition, x square under root, that will be x mod. So c mod should be less than 1. For Lax-Wendroff, it means that for Lax-Wendroff method, the current number should be less than or equal to 1. That's what we have proved. Thank you for watching.